Coming to the next topic, it is optoelectronic devices. What is the optoelectronic devices? Which is nothing but mostly the light is used on a semiconductor devices. Till now, so far we have studied about the junction diode. The junction diode is mostly operated under forward bias because it allows current only in one direction. So, and a special type of junction diode is used on which a light is fall. So, when a light of suitable frequency falls on this junction diode surface, there is some changes. So, such devices are called optoelectronic devices. So, the carriers are generated. What are carriers? Carriers are nothing but electron hole pairs. So, carriers are generated when a photon strikes on a diode. So, such devices are called optoelectronic devices. Okay. So, the electron hole pairs are generated. So, this is called the carriers. So, the carriers are produced when the photons, which is nothing but a light of suitable energy, that is E is equal to h nu, a light of suitable frequency that is falls on the surface, then the carriers are produced. So, the main principle is photovoltaic effect. So, the main principle of these optical electronic devices are photovoltaic effect. So, the principle is photovoltaic effect. 11th lesson we have studied, no? Yes. Photovoltaic effect. So, under the optoelectronic devices, we are going to see the three junction diodes. The first one is a photodiode. Photodiode. So, how the photodiode looks? It is nothing but a simple, what is it? A simple PN junction diode. Listen. It's nothing but a simple PN junction diode. So, this is P region, this is N region. It is, the PN junction diode is covered with, the upper layer is covered with a transparent window. So, this is a transparent window. But only one thing, the junction diode is operated not in a forward bias, reverse bias. So, the P side should be connected to negative terminal and the N side should be connected to positive terminal along with the resistor and the micrometer, because reverse bias means micrometer only we use, no, yes. So, negative terminal, positive terminal, this is low resistance and this is micrometer. Actually, in this photodiode, the intensity of the incident light that plays an important role. Incident photons that plays a very important role. So, this is a construction of PN junction diode. So, a specially fabricated PN junction diode with a depletion layer, but it is operated under reverse bias. Notice that it is reverse bias to PN junctions. Okay. So, that P side should be the negative, N side should be the positive. And the upper layer of the diode is covered with a transparent window. Now, when a light of suitable frequency that is allowed to fall on this surface, what happens? Photo excitation takes place, that is photons of suitable frequency falls on this transparent window, then the electron hole pairs are induced. Okay. So, due to the inducing the electron hole pairs, the electrons are moving to one side and the pairs are, holes, the holes are moving to another one side. So the depletion layer width is reduced. By reducing the depletion layer width due to the electron hole pairs on every side, because from P side the electrons are moving towards N, and from N side the holes are moving towards P regions. So the barrier width is reducing, in which the current is induced. So with the help of a light on this special reverse bias PN junction diode, the current is induced in the circuit. Such devices are called photodiodes. So important point we should notice, it is operated under reverse bias. Okay, and when the photons of suitable energy falls on this surface, the electron hole pairs are generated. That is a charge carriers. So the generated charge carriers, that is electrons from the P side, it's moving towards N side. At the same time, the holes, the positive charge, that moving from N side to P side. So under equilibrium, the depletion width is reduced. So by reducing the depletion width, there is a EMF generated. Okay, so this EMF is measured by the micrometer. Hence, the light energy is converted into electrical energy. And this photodiode is used in burglar alarm and many fire alarms and so on. So even in our day-to-day life, it is used in variety of our regular applications. Mostly in a burglar alarm, that is in a bank and some shopping malls, then TV remote control systems. So all used under photodiodes. And also it is used for counting, it is used in a counting devices. How many persons are entered into the auditorium and how many persons are leaving out. So all can be measured with the help of a photodiode. The second optoelectronic device which we are going to study is LED. That is a light emitting diode. The second optoelectronic device is light emitting diode. That is LED, light emitting diode. Okay. Actually, LED is nothing but a specially fabricated PN junction diode. It is operated under forward bias. And one more thing I forgot to say, the intensity. It is a reverse bias, no, for photodiode. Listen, I forgot to explain the graph. In a reverse bias, the reverse current measured in microampere. So if the intensity, I forgot to say about the intensity. If the intensity is increased, what happens? Greater the intensity, greater the production of photocurrent. For a small intensity, the small photocurrent is. If the intensity increased, then the photocurrent also increased. So depending upon the intensity, the amount of photocurrent also increase. Okay, so greater the intensity, greater the photocurrent. This is voltage, this current in milliampere, this is also voltage. But the photodiode is operated under reverse bias, no? So in a reverse bias, greater the intensity, greater the current is produced. That one I forgot to say. Now we will switch to LEDs. So LEDs are nothing but, it's a specially fabricated PN junction diode. It is a specially fabricated, that is heavily doped PN junction operated under forward bias. Okay, so basically we know LEDs are, every homes have LEDs. Most of the indicator lights are LEDs because it consumes less power. It operated at very low voltage. It gives more amount of light. Yes. So the LED looks like this. So inside this cylindrical transparent glass window, the two electrodes are there. The electrodes are attached with the semiconducting medium. So one is a positive, another one is negative. The two electrodes are there. Okay. When external potential is given, then the light is emitted. Depending upon the semiconductor medium, the nature of the spontaneous emission is different. Okay, if you for a different semiconducting medium, the different lights are emitted. So, how for a different semiconductor medium, the different colors we are going to see. Before that, the diagrams of the LED. And one more thing, in LED, the symbol. It's a specially fabricated, heavily doped PN junction. No, so it's a PN junction diode, but it emits a light. Okay, it emits a light. This is LED, the P side, it's the N side. This is a symbol of LED. LEDs, this is a symbol of LED. Then one more thing, in this LEDs, the energy of the emitted photon, that would be approximately equal or less than the energy gap. Okay, for that we should choose a specially doped substance. So depending upon the doping, the emitted photon energy is different. The emitted photon energy approximately equal to energy gap of the semiconducting medium which we have chosen, or somehow less. Okay, and initially when the terminals are connected to the external potential, the electron hole pairs are generated. Okay, so the electrons are moving from N region to P region. At the same time, the holes are moving from P region to N region. But at the junction, under equilibrium, there is a recombination occurs. At junction, the recombination occurs. The recombination of electron hole pairs occurs. So that emits light. Okay, in the form of some radiations. Okay, so the working is very simple. Notice that when the terminals of the LEDs are connected to the external voltage, due to the external voltage, the electrons from the N side moving from N side to P side, and from the P side the holes are moving towards the N side. But at the junction boundaries, the depletion layer, here the junction boundaries is nothing but depletion layer, the recombination of electron hole pairs occurs. With the recombinations, the emitted photons are released. Okay, I repeat once again, from the N side, the electrons are moving towards the P side. Then from the P region, the holes are moving towards the N side. There is a depletion layer. From the depletion layer, the recombination occurs. With this recombination of electron hole pairs under equilibrium situations, the photons are emitted. It's a very simple process. And already I told, depending upon the doping substance, the emitted light color is different. Yes. So based on the doping, how the color is different, we'll see. So for a visible light, for a visible LED, the energy gap should be roughly 1.8 volt around. Okay, so that the spectral range must be, the spectral range of this LED must be 0.4 micrometer to 0.7 micrometer. That is from 3 electron volt to 1.8 electron volt. Okay, and I told based on the dopant, their color emission is different. No, yes. So for a gallium arsenide phosphide, and the energy gap, yes, this is a common formula. So this is a doping substance in which the gallium arsenide is 0.6 and for phosphide is 0.4. For operated with an energy gap of 1.9 electron volt, it emits red. Okay. Similarly, we have gallium arsenide alone. For gallium arsenide dopings of an energy gap around 1.4 electron volt, it emits infrared. In our TV remote controls, we use the infrared. No, on mobiles we have Bluetooth, that is ultraviolet. But TV remote control system, TV remote, AC remote, and most of the remote devices uses infrared. For that, the LED is doped with gallium arsenide alone. If you want only the red LED, then additionally the phosphate should be added. So in a gallium arsenide phosphide with 0.6 and 0.4 with an operating energy gap 1.9 electron volt, the particular LED emits red light. If you have only the gallium arsenide dopant alone with an LED and it is operated under 1.4 electron volt of energy gap, it emits infrared. Similarly, we have some different colors LED, red, yellow, orange, and blue. So all the different color LEDs that emits a different color, it's due to different dopant. Okay, if the dopant level varies, then the emitted color also differs. But the two examples alone, you notice it, and from that there is a possibility of asking 1 marks. Okay. Next, we are going to study the last optoelectronic devices, solar cell. We know in our school building also we have a solar cell, and some calculating devices also solar cell, and satellite also used a solar cell. So the solar cell is a device on which when a light of suitable frequency falls, it generates the EMF. So current is produced. So light energy is converted into electrical energy. So how a solar cell operates? Look at the solar cell. The working principle of solar cell is photovoltaic effect. The working principle of solar cell is, already we know, it is photovoltaic effect. And the symbol is given. Look at the symbol very carefully. It is nothing but a specially fabricated PN junction on which a light of suitable frequency falls, it generates an EMF. It generates EMF when a light strikes. Okay. And another one thing we should notice, the energy gap and the energy of the incident photon. The energy of incident photon and the energy gap in the cell. Yes. So the energy of the incident photon should be greater than the energy gap, or otherwise no EMF is generated. Now the construction, how it looks, listen. So for that we take a P region or P wafer. This is a P wafer of silicon. Okay, and the thickness is about 300 micrometer. And the upper layer of the P regions, a small N region is created by diffusion process. Okay, the upper layer of, this is a P, and the upper layer of the P regions we are created by diffusion process, that is N region. The thickness is about 0.3 micrometer. This is very, very small. Okay, mostly we have a P side. On that we are doped the N. By doping we have created a N. The thickness is relatively very small. Okay, then it have a two contacts. One is a front contact, another one is back contact. So on the back contact, full of metal region is connected. The back contact is completely connected with a metal. So this is a back contact. and this is a front contact, but front contact is connected with the okay, and the front contact we have some metal fingers. All the metal fingers are externally connected and we are taken out. Okay. Okay. So on the front contact, this is the metal fingers. That is in the top layer, that is a front contact. And in the back contact full of metals. Mostly we'll use a silver metal. That's why the solar panel cost is high. Okay. So all the metal fingers are externally connected, and here one output. Then the back contact we have another one output. Okay. So this is a construction of solar cell. In a single solar cell, how it is fabricated? First, we should take a P wafer silicon with a thickness of 300 micrometer, on which we are by doping process, by diffusion. Under what process we have created? By diffusion. By diffusion process, the dopings are added. So we have created an N region. So N is the top region, which is upon the P, and the thickness is 0.3 micrometer. Then there are two contacts, back contact and the front contact. Back contact is completely connected with the metal. Okay, and the front contacts have the metal fingers. Then the metal fingers are externally connected and taken out. Okay. So this is a construction of what? Fabrication of solar cell. Now, this is placed or exposed to the light. When the sunlight, which is allowed to fall on this, when sunlight is allowed to fall on this, what happens? Due to the energy of the photons, due to the energy of the photon and the energy gap, this is the energy gap. So the energy of the photon should be greater than the energy gap. Then there is a, what to say, yes, three process takes place. Here, when the sunlight falls on this surface, there are three process takes place. One is generation, separation and collection. Generation, separation and the collection. So these are the three important processes carried out on the solar cell panel. First, generation. What is the generation? What it generates? It's nothing but carriers. The electron hole pairs are created. The electron hole pairs are generated. When a light of suitable energy strikes on this metal surface, then the electrons are moving inside the panels. The electrons are moving towards the N side. Electrons are moving to N side. At the same time, the holes, the vacancies are moving to the P side. Okay, so these are all electrons. So all these are electrons and these are all holes. Okay, so the holes are through the depletion layer. The electrons and the holes are moving to the regions. Okay, so here electrons moving from P to N and the holes moving from N to P. So under equilibriums, the N layer should be negative. Okay, here the N layer should be negative and the P side should be positive. So that is called collection. So N is being negative with the maximum electrons. Okay, at the same time, P should be positive with the maximum holes. So there is a concentration gradient, so from which the output is drawn across the terminal. The output is drawn across the terminal. So the another one simple diagram we are going to draw. See that the same diagram. So mostly it's a P, and upon the layer we have a N. Okay, and here we have a metal contact, and these are all metal fingers. Then on this metal fingers, the energy is incident. It's a very simple diagram. So mostly we have a P wafer of thickness about 300 micrometer. N wafer of thickness is just 0.3 micrometer, and these are all metal fingers. And this is at the front contact. Then at the back contact of the PN region, we have a metal contact. So across this front and back contact, the output EMF is drawn. EMF output is drawn when a light of suitable energy that strikes on the surface. So this is how the solar cell panel works. And mostly it is operated in a fourth quadrant. So how the graph looks? Listen. In the solar cell panel, it is operated on the fourth quadrant. Okay. So 1, 2, 3, 4, fourth quadrant. So in the fourth quadrant only the solar cell output is the EMF output. So this is the curve, IV characteristics curve of the solar cell. So this is a voltage. Okay. So this is a carrier voltage of this curve. That is the open circuit voltage. Yes. So this voltage is called open circuit voltage, and this is a current, that is closed circuit current. Okay. So it is in the fourth quadrant. They may ask in a 1 mark. So the IV characteristics of the solar cell in which quadrant? No, fourth quadrant. Okay. So the IV characteristics of the solar cell is fourth quadrant. Then mostly for an ideal solar cell panel, we should choose the energy gap that should be 1.5 electron volt. So this is ideal for the fabrication of solar cell. So this energy gap, the material should have the energy gap which is equal to 1.5 electron volt. So this would be the ideal, that is very suitable for fabricating the solar cell panel. And we have a different semiconductor device. No, yes. For silicon, this value is 1.1 electron volt, and for gallium arsenide solar cell panel, it is 1.43 electron volt, and cadmium tellurium, it is 1.45 electron volt, and for this compound, copper, indium, selenium 2, this is 1.04 electron volt. Okay. So for different materials, we have the different energy gap, but from which the suitable solar cell panel energy gap is 1.5 electron volt. So for a different semiconductor substance, we have a different energy gap, but among this all, this is a suitable cadmium tellurium we may choose. Okay. Then one more thing on the surface, we should notice another one thing. On the surface, how much light is exposed from which the electrons are produced, no? Yes. So that is 10 to the power 4 centimeter inverse, which is used for high absorption of light. So even though we have fabricated a solar cell panel, but on the surface, on the N metal surface, no. So this should be 10 to the power 4 centimeter inverse. So in every centimeter, at every centimeter of the panel, 10 to the power 4 amount of light should be there. Then only it absorbs the more amount of light, so the EMF also induced. So like a photovoltaic cell, the first case, this also depends the intensity. So greater the intensity, greater the amount of light, but up to a saturation point. Okay. So this is how the solar cell panels are fabricated, and the uses of the solar cell panel, it is in the variety of uses. Okay. It is used in satellites and also space shuttles. Then some calculating devices, that is calculator. So all have a Casio brand. You can see the calculator at the top corner of the calculator. You can see the black panels. This is nothing but solar cell panel. So if the cell is not, if cell is fused, even the room tube light is enough to operate the calculator. So the calculator not only operated under the sunlight, even whatever the light, but I mentioned the range. The range should be, yes, there must be the range, within a visible range, whatever the light is incident on the surface, the solar cell can be operated. Thank you.